Hello, everyone. My name is Carl Diaz. I'm with the Learning Resources Center here at the University of Colorado, Denver. And today we're going to talk about inertial frames of reference. Again, this is something that I think professors don't focus on a ton. They're not like, oh, you have to know, they don't test you on it, but it's something that they want you to understand and be aware of. And if you've taken a physics class, you should know what this is. So let's talk about it because I'm sure you've heard about it, right? So first of all, just to state it, right, when we say like what is an inertial frame of reference, it's a reference frame where Newton's first law is valid. That's the meat and potatoes of it. Okay, right here. Okay, that's what an inertial reference frame is. It's a reference frame where Newton's first law is valid. But what does that mean? We'll figure it out. And just to remind us, I wrote Newton's first law summed up very simply, and the things that we actually just need to know for inertial frames of reference is that when we have no net force, the object should either. So let me say that better. When there's no net force applied to an object, then it should either have no motion, right? It should be stopped, or it should be moving with constant velocity, okay, where its speed and direction isn't changing, okay? That's what Newton's first law is. So when no net force is applied to an object, either the object should remain at rest or be stopped, or it should be moving with constant velocity, no changes in speed or direction, okay? So what does all this have to do with inertial frames of reference? Well, let's start with the bad inertial frame of reference, because you'll kind of see what's going on here. And then when we look at a good one, you'll be like, oh, that makes perfect sense. Like, yeah, that's how it should be. So let's say that this is you, right? You're in a bus, okay? And let's say you're at a stop. You're at a stop sign. Okay, and there's this person at the front of the bus on wheel skates. They're just standing, wheel skates, roller skates, and the bus is stopped, but the minute that the bus starts to move, that person's going to start rolling around on the bus, right? That's common sense. They're not holding on to anything; they're just standing there in their roller skates. Well, sure enough, the bus starts to move. And what starts to happen? Well, the person, right, that's standing at the front of the bus, and initially, right, the velocity of that person was 0, right? They weren't moving. They were stopped. Okay. And then what happened? Well, the velocity of not only did they start to move, but they're speeding up. They're speeding up. And what does that mean? Well, keep in mind, if you don't know what that means, you should know Newton's second law. And if an object's speeding up, that means it has a net force applied to it. Right? And we can kind of inference that from Newton's first law. If Newton's first law is that there's no net force, which means the object should be stopped or constant velocity, which means if an object's speeding up or slowing down or changing direction, that means there must be a net force on it, right? So this person in the skates, right? The bus is moving forward, right? But we are sitting in the bus with the person, right? We're moving with the bus, essentially. So to us, it feels like, right, if we were to look down at the ground in the bus, not outside the window, imagine that, all the windows are closed, okay? Imagine we can't see outside the bus, okay? So when we look around inside the bus, everything's sitting still, right? And if we look at it looks like, like I said, if we can't see out the windows, besides the roar of the engine, it looks like the person's the only thing moving. We can't even tell if we're really moving or not. Right? But it looks like the person's moving, the person's speeding up. It doesn't really feel like the bus started to move, right? When we're sitting in it. And so as that person starts to move towards us, they start to speed up. And then at the end, they make their way to the back of the bus. Well, this is a bad inertial frame of reference. Why? Well, when we draw a free, let's take this example right here. Okay, well, I don't know why I erased those. Let's draw a free body diagram on this person. Well, we know that person has weight, right? And then we know that they're touching the ground, so the normal force is there, because normal force is a contact force, right? Anywhere you make contact, the normal force is going to be applied to you in the perpendicular perpendicular to the surface, right? So in this case, we're touching the ground, so the normal force is going to apply first. Are there any other forces here? Now look, we have we're saying that this person's accelerating. So to us, you should be saying, yeah, there should be some other force, in this direction, right? It should be in the same direction as acceleration. Like the net force should be, that's the thing that the net force is the thing that makes you speed up or slow down or change direction, right? Acceleration is just a measure of that. But when we see that we're speeding up, we know we have acceleration. And if there's acceleration, that's a way to think of that backwards is to say, well, if I have acceleration, there must be a net force there. But there is no force in this direction on this person. This person just has their roller skates on. They're just rolling to the back of the bus. The only force that this person has is its weight. It's standing on the ground, and then the normal force is pressing back on them. So that's the other force on them. But there's no force, in the direction that they're moving. So to us, this person is in equilibrium, right? There's no net force on them. If we were to do all the net forces, right? If we sum the forces here, right? We know that it's going to be equal to, well, let me write that a little bit better. If we sum the forces here, we know it's going to be the normal force minus mg, right? They're not, it doesn't matter if up is, let's say up is positive, down is negative, okay? So we know that the normal force is going to be minus mg, but we also know that they're balanced, right? We know that they're in equilibrium because the person isn't flying up through the air, right? The normal force isn't larger than weight. If it was, the person would be up in the air, and the weight isn't larger than the normal force. If it was, then we would be breaking through the ground of the bus. But we're balanced on the ground of the bus, right? We're balanced on the ground of the bus. So that means we're in equilibrium, right? And again, there's no other forces. So this is the forces here. So the net force on this, if we do the math, since the normal force and weight are the only forces on this person, that means that the net force is equal to zero. It's equal to zero, which means this person is in equilibrium. You might be saying, oh, well, Newton's first law is valid. No, that's bad. Newton's first law isn't valid because remember, if there's no net force, this person should either be stopped, not moving, or moving with a constant velocity. But they're speeding up, right? Speeding up is not a constant velocity, right? Constant velocity is where your speed doesn't change. It stays the same, and your direction stays the same, right? But this person is speeding up from the front to the back of the bus. So right? But they have no net force on them. So Newton's first law is just not valid. It's not valid. The physics doesn't make any sense. It's like, how is this person speeding up to the back of the bus, right, when there's no net force applied to them? The only forces that are there are the weight and the normal force, right? So this is a bad inertial frame of reference. It wouldn't be good to try to measure or try to look at the forces and how they're related to like the person on the roller skates, how the forces are related to this person's motion. They wouldn't make sense. We'd look at it and be like, well, this person's in equilibrium, but they're speeding up. So it's a bad inertial frame of reference. It doesn't give us good physics, okay? But what's a good inertial frame of reference? Well, now let's say we're standing outside the bus. We're no longer sitting inside. Let me go back here. One more thing I wanted to say. And another reason why this is a bad inertial frame of reference is because we are accelerating. That's really the idea, okay? Is that bad inertial frame of references aren't good when let's say we're trying to do the measurement. We're trying to measure, right, this person, or we're trying to figure out, relate the forces on this roller skater to their motion, okay? But if we ourselves are accelerating and then trying to make that measurement, if we're speeding up, but then looking at an object and trying to figure out how fast it's going based off the forces, we're going to get bad answers. That's what this is telling us. And again, how do we know? Because the person, even though it looks like they're moving, they're actually not, right? They're standing still. It's the bus that's moving forward, right? But to us, since we're accelerating with the bus, it looks like to us that the person with the roller skates is accelerating. So that's bad. That's bad. We would get really bad measurements that way. So an inertial frame of reference, what makes it a bad frame of reference is when you have acceleration. from the measuring point where you're the person trying to measure what's going on, but you yourself are speeding up or slowing down. That's a bad thing. So what's a good inertial frame of reference? When you're standing still. The person who's making the recording or trying to record or trying to, come up with, relate the forces to the motion of an object, it's best if you're trying to do those calculations and make those recordings and figure out what's going on, is if you're standing still. You have zero acceleration, or you could be standing still or moving at constant velocity. We'll talk about that here in a second. This example, and it's the best one, is when we're standing still. Like you'll always hear like Earth is the best frame of reference. Earth is the best inertial frame of reference. Why? Because even though Earth's spinning on its axis and yes, moving through the solar system, and the sun's pulling us through the galaxy, all this motion, right? None of that stuff, we can't feel it so much, right? And the effect on us is so insignificant. So to us, when we stand on the ground, we're essentially at rest. And when we measure things around us in reference to the ground, right, in reference to the ground that we're standing on, it's a good inertial frame of reference because we're standing still. The Earth is standing still. It's not moving relative to a car moving, or the Earth is staying still. When you start to walk, it looks like the Earth stays still because you're able to walk away from a certain point, right? Like if you're here, right, and then you start to walk this way, well, this is your start position. Now you're over here, right? Now you're over here. Well, you're not at your, it looks like the Earth stood still, right? This is where you were, and somehow you ended some distance from that spot. So it looked like you moved and the Earth stood still, right? And that's essentially what's going on. So that's why the Earth, when you're standing on the ground, is the best frame of reference. And that's what this is trying to show you. Okay, so let's say the same situation. So here the bus is stopped. I forgot to write this, right? And then here it starts to move or speed up. And it's continuing to speed up here. Okay. Continue. Sorry that's sloppy, but it's just really giving us reference. Starts to speed up. Right? So we're at the beginning. We're stopped. Right? Number one, right? We're stopped. And we're standing outside the bus, and our velocity is 0. The bus's velocity is 0. The skater's velocity is 0, right? Well, now the second situation, right? When we look at frame 2, right here, right? We can see that the bus is starting to move. Just like this is the same situation. We just are standing outside the bus now. So now, right, in our first situation, the bus was stopped, and then the bus started to move, but it looked like the person was speeding up in our first situation. Well, here, everybody stopped, right? And then the bus starts to move. But from this situation, we can actually see the bus moving, right? We can actually see the bus starts to speed up. And what we notice is that the person inside, I don't know what I'm doing here, the person inside, right? It looks like to us, and that's why I kept this measurement here, they don't move. They continue to stay 3 meters away from us as the bus moves to the right, right? As it starts to speed up to the right. So to us, right, it looks like the person staying still, right? They're not moving. They're standing still. And the bus is moving. It looks like the bus is moving, right? To us, when we're standing outside the bus on the Earth, standing still with 0, right? We never move. We're always going to be standing still in every situation, right? And so this is a good frame of reference, right? Because look, let's again take this middle situation. If we were to draw a free body diagram on this person, well, again, there's the norm, right? We know, well, I do those backwards. Let's do those in the right order. Right? We know this person has weight. They're pressing on the ground. And because they're pressing on the ground's going to press back on them with the normal force, right? And that's it. Those are the only forces that are on this person. There's no one's pushing on this person, right? There's no, just like in the last one, there's no force on the person to the left, right? But in the previous example, even though there was no force on the person to the left, there's no one behind this person pushing them or something, right? There's no force this way. They were speeding up. But here, when we come over to this situation, there's no net force on this person, but they're also not moving, right? The velocity of the person inside, the skater inside, is 0 as well. This person, they're 0. They never move. Their velocity remains 0 through the whole motion of the bus. It's the bus that's moving. So that means Newton's first law is valid because this person right here in the bus, they're not moving, right? They're not moving. Let's make sure everything's correct here. Their velocity is 0. Their net force, if we were to sum their forces, right, it'd be the same. It'd be normal force minus mg, but we know they're equal and opposite because the person's balanced on the ground, so we know they're going to be equal to 0, right? So we see here, right, that the net force is equal to 0, but look, this person also has 0 velocity, so that means Newton's first law is valid. Remember, if a person has, or an object has no net force on them, their velocity should either be 0 or should it remain constant, which means it's not changing speed or direction. Well, in this case, this person, no matter where they're at as the bus moves to the right, their velocity remains 0. The only time that they start to move with the bus is when the back of the bus, right? So like the very next situation, right? This person would be touching the back of the bus, right? And the bus would be pulling them with them. But look, now the bus is applying a force to that person because they're touching the back end of it, right? So that's why the bus is pulling them now. Now the person is now starting to move with the bus and has some velocity to the right, right? But until that point, until the bus makes its way far enough to where the back end of the bus makes it to the person, that person's just going to remain, and we can see their position. We can see that their position remains the same, right? This is their initial position. You can see it never changes. They stay at the same, right, initial position the whole time. Okay? So this is a great frame of reference, okay? Newton's first law works out. There's no net force on the skater inside the bus, and they're not moving. Where, look at the bus. The bus is speeding up. We can see the bus speeding up, and we know there's a net force on the bus. The person in the bus is stepping on the gas pedal, right? That gas pedal is providing some sort of net force on the bus so that it moves forward, right? And that net force is causing the bus to speed up, which is what the acceleration is telling. So the velocity is changing. So everything works out. The bus has a net force, okay? And that's the thing speeding up. So that makes sense. That follows Newton's second law. And the person, the skater, who has no net force on him in the bus, well, they remain still. They don't move, right? Which lines up with Newton's first law. Newton's first law says no net force, no motion. So that means that this, when we're standing still on the surface of the earth, like standing on the ground, that is the best frame of reference we can have. But you'll hear this, is that you'll hear, right, and this is where we're not moving, right? But you'll also hear, like, if an object's moving at constant velocity, that's a good frame of reference as well. And the reason why that's okay, I'm not going to get into the details here because that's just making this more complicated than it has to be, okay? This is what you need to know. But if an object's moving at a constant velocity, well, relative to me, like let's say there's this object over here, right? And it's moving this way, but the velocity is constant. Okay, the velocity isn't changing. It's moving, but its speed isn't changing and its direction isn't changing. So that means, like, I don't know if you should have discussed it in class. I have a video on it as well if you need to watch it, but relative velocity, right? So the relative velocity between this object we'll call, V1, and me, we'll call me V2, right? It remains constant. So if the relative velocity remains constant between someone who's standing still on the ground and an object that's moving, then the object that's moving is also a good inertial frame of reference because it's not speeding. Remember, I said it has to do with acceleration, right? The person who's recording cannot be accelerating. And so if the person's moving at a constant velocity in this like car over here, well, they're not accelerating. So they're gonna get a good measurement. To them, it's gonna look like the person's standing still and the bus is moving. To me, standing on the ground still, it's gonna look like the person standing still but the bus is moving. So everything works out. Newton laws are valid. And that's an object moving at constant velocity where its relative velocity isn't changing relative to me, right? Or someone sitting on the ground still, then that's also a good inertial frame of reference. So hopefully this was helpful. I hope it was. There's not much more to say here. Just make sure that you you know, it's kind of a complicated thing. And this inertial frame of reference, this is why Newton's first law is called law of inertia, right? So the law of inertia, you might hear Newton's first law called the law of inertia, and this is why, right? Newton's first law dictates what an inertial frame of reference is, right? And so because of that, it's known as the law of inertia. So that's the connection there. But hopefully this was helpful. I'm super proud of you all. Keep kicking butt at school. Keep kicking butt in the rest of your classes. And I'll see you on the next video.